Okay, so last time we reviewed the idea of trying to implement the optimal rule, sometimes referred to as the Bayes rule, for real data. So if you have real data, you try to basically have a training data, and then you try to find an estimate of the joint distribution using, let's say, a sample of size n from your joint distribution. And then once you have the estimate of the joint distribution, you can compute the conditional probabilities and then find the optimal decision rule. So we went through this. There were some notations that it used. Hopefully people are comfortable with now. We're going to use this type of indicator notation a lot. So to estimate the probability, the joint probability distributions, we average the number of cases where, not the average, but yeah, take the average over all the cases in which the conditions happen of these indicator functions. So this average of indicator function, which is a proportion. So this is the count of how many cases they are, and then divided by n. And then from that, you can calculate this p-hat of y given x. And then the decision rule, the optimal Bayes rule would be, it's not optimal, but an estimate, which is called the plug-in estimator. So I plug in my estimate of the probability into the rule that I had, which was just the population probability, and I get f-hat. And then we saw that this can be written as this. So this is the same rule expressed in terms of the so-called regression function, which is this probability of y being equal to 1, or estimated probability of y being equal to 1, which turns out to be also the expectation you will show would be empirical expectation of y given x. And so we thresholded at 1/2. So let me see if you guys remember. So why did we threshold it at 1/2? Let's see if you guys are following. Why these two are equivalent? So what I do is, like, I find for every x, I choose the decision that maximizes the probability of y being equal to that decision given x. So y would be this equal to this. No one remembers. So this probability, I have to compare the probability that y is equal to 0 given x, right? And should decide which one is bigger, right? And they sum to 1. So the one that's bigger than 1/2 is going to be bigger because the other one is 1 minus this. So that's why we threshold at 1/2. If you change your loss function, so this was the optimal rule for the 0-1 loss, if you remember, which led to the risk being the misclassification rate. So if you change your loss, I might assign it as a homework problem. I don't recall if I talked about it or not, but I think we talked about it. So if the loss function is like that, but L01 and L10 are different, then the rule will be similar. And there's a homework problem at some point you might see it, but this 1/2 would be different. The only thing that changes would change the relative cost of misclassifying 1 or 0. So in the 0-1 loss, if you remember, we had this actually in the notes that I sent, the y and y-hat are flipped. So I'm going to use the notation of those notes. So ly-hat, and this was the 0-1 loss. It says it doesn't matter whether I make a mistake on a 0 or 1. So if y is 0, I mistakenly say it's 1, or if y is 1 and mistakenly say it's 0, I pay a price of 1. But if you change that, you can go through the argument that we went. You get a different thing here. So you get, instead of posterior, you get the expected loss. You want to minimize the expected loss, and then the result is the same rule, but with these 1/2 being replaced by something else. Just a comment. Maybe we'll see it later. Okay, but that's for now. This is going to be our rule, and you felt happy with this? Sort of remember. And then we showed that in this example, if you go through the entire training data, you can calculate, this is basically eta hat for different values of x. X was a single variable, takes 2 values, female and male. And basically based on these values, we can threshold these values of 1/2. So if bigger than 1/2, the decision would be 1. So this is 1 here and 0 here. And this is summarized in a decision tree like this. We went over this. We'll come back to something similar later, but this is an implementation of the optimal rule in real life. Okay. I'm going to skip this for now again. And then we ended up towards the end of the last lecture, we started talking about the so-called training error, how we can measure the risk or estimate an estimate of the risk. So we have an estimate of the rule. How do we estimate the error? And we talked about this sort of the idea of training error. And so what was the training error? See if people remember. So if I give you a classifier, let's say f hat. So for example, my classifier turned out to be something like that. Let me switch to the other set of slides. While you think about back here. Yeah, suppose my classifier is f hat of x is 1 if x is female, 0 if x is male. So that was the conclusion of the classifier that we trained. It turns out to be the same as the one that we use, the population level probabilities. So that's my classifier. How do I measure how well I'm doing? We did a calculation of the error under the assumption that we know the true distribution. But now I'm assuming that we don't know it. We just get the training data and we computed our rule. It turns out to be this. How should we measure the performance? And I calculate the misclassification rate, or an approximation of the misclassification rate. So let's say this is the data. Right? I have a rule, classify. How can I measure how well I'm doing? Yes.
Look at number of misclassifications.
Okay, so how do I do that?
Would it be 1 y hat I as well?
1 y hat I not equal to y I, right? Okay, and then I take the average, right? And then y hat I is just gonna be f hat of xi, right? So I'm gonna apply my rule to every one of these. So my rule was f hat of x is 1, 0, right? X is female, X is male, right? I'm gonna go apply the rule. Just look at this, right? So this is my yi. I'm gonna create a y hat I here. So this is male, so this would be 0, male, 0. Now female would be 1, right? Male would be 0, 0, 0, 0, 0, 0, 1. Right, that's my prediction. This is the true Y, and then I compare. Right. And then the difference, basically, this is saying, in this case, this is like indicator of Y hat I. Let's do this. Indicator of Y hat I, this is another column. What would it be here for the first row? Yeah, so this would be 0. What I'm saying is like this line, right? I just want you to understand what the indicator is, right? The indicator is saying if Y hat is not equal to Yi, then it's 1, otherwise it's 0. So here they're equal, so this condition is not satisfied, right? So this is going to be 0. Here it's going to be what? This is going to be 1. Here it's going to be 1, right? Here it's going to be 1, okay? 0, 0, 0, 0, 0, 0. Right? As long as they mismatch, we pay a price of 0. So you get 3 mismatches. Let's say my entire data for now is 10, for example. Just we have this 10 lines. So what would be the estimate of misclassification rate? What would it be? 0.3, yeah. So I'm going to call this R training hat of F hat. And so this would be for us approximately 3/10, which is 0.3. If you care about just exactly this, if you care about this 10 lines, so you get 30%. If you recall what we did with the population level was 0.22. Now it's 0.3. It's not a good, not okay, yeah, but not good. Yeah.
For the predicting function of F hat, is that always going to be the one from the majority rule or the optimal?
This is not the majority rule. If you remember, the majority rule ignored, right, the features. So the way that we drive this last time, so if you recall, we went through the calculation here, right? So this is not the other. Yeah, so we went through the calculation. So you calculate these probabilities and then form these conditional probabilities, right? And then decide. So this is the given 1/2. So for males, this is actually this is probably a 0. So the probability of 0 is the given 1/2. So we would say 0 actually. So probability of 1 would be like 0.25. So we condition on the X, right? So this is not the majority rule. If you do majority rule, you can also get an estimate of the majority rule. How do you get an estimate of the majority rule? We didn't do, we did the majority rule at the population level, but at the data level, how do we do majority rule? Let's say if I want to do majority rule just based on the 10 observations here, what will be the majority? Yes.
Count the number survive and see. So you say that there's 7 zeros and 3 ones, because there's more zeros than ones, then we would just label everything as 0. We predict it.
Yeah, so basically you look at the majority label. Majority label here is 0. You ignore everything, this majority label and Y. Right? If you want to be like formal, we calculate the p hat. What is the estimate of the probability, the marginal probability of Y being equal to 1? That would be 1/n indicator I from 1 to n. Yi equal 1. P hat Y equals 0 would be like the same thing with 0 here, but you don't need it. It's going to be 1 minus P hat. Y equal 1. Right, so this is like this count would be how many ones we have? 1, 2, 3. Right, so this would be, is it, yeah, 3.10, but like 3/10.3. So the other one would be 0.7. So the one that's bigger, so we look at, we take the decision. So arg max, I just want you to get comfortable with the notation. The idea is very simple. just what Alex mentioned. So argmax would be, that's the majority rule. Let's call this f hat 1. Doesn't depend on x actually. So this turns out to be 0 no matter what x is. Right. We actually can discard x. It's just going to be always 0 for whatever feature you want. The decision is always 0. Right? Ignores the features. Basically count how many label is in the majority. Here 7 out of 10 are 0, so we go with. So this is the majority. Is that clear? So what was your name, by the way?
Tila.
Tila. Tila. T or J?
Tila, yeah.
Tila. Okay. Is that clear?
Yeah.
Right. Okay. So this is different than the majority rule. Both the majority rule and the optimal rule we can approximate. And how this is the approximation of the error. So we call this the training error. So anyone knows why we call it the training error? Yes, let's see if anyone else knows. Go back to. Okay, so why?
Because you're basically testing the data you used for collecting the previous assumption. So the PY for 1 given is a female. You're using that current data to predict that. So you're going to use another set of data to test if those values are correct. So you need to like check your training data first.
Okay, okay. Good. What was that? Yeah, so you want to also say?
It's kind of the same thing, like, this gives us the percent chance in which the predicted value is erroneous. I think it's like the error in our training data.
Right. So the reason, yeah, these are all like, right. I'm just gonna wanna like emphasize that the reason why it's called the training error because it's calculated on the training data. Why we call this the training data? Because we use it to train our classifier. So your classifier uses this exact data set. Right. So you use the data to obtain your decision rule. Again, if you go back to probabilities that we calculated to arrive at that rule, the conditional probabilities, the joint probabilities, all of them were you're using this calculation here. So you went over like all the male cases and found the proportion of the survived ones, and then over the females as well. So this is using the data to calculate those probabilities. Those probabilities went into constructing your classifier. So the classifier depends on the training data, and you're evaluating it on the same data set, which is the training data. Okay, so it's called the training error. Training error. Because it is calculated on the training data. It's like tautology. Okay, the same data set used to train the classifier. So training the classifier is just a fancy name of like constructing the classifier using the data. With the language in machine learning is trained. You train, usually there is a model that we have. You try to fit it to the data, and that process is called training. But basically driving the classifier from data, that's called training. Somehow using your data to pick a classifier. So you trained on the same data set. So the data set on which you train is called the training data. And then we use the same data set to evaluate the performance of the classifier. So that's why it's called the training error. It's the error of the classifier on the training data. Okay. Does that make sense? And it turns out to be 0.3 here. Questions? So let me go there. So here's a definition for a general classifier F hat. That's our training error. I'm going to use R hat train. R was the risk. So if I have, let's say a general classifier F, classifier as a function, my population error or population risk was something like, this was the loss, remember? So, which is P, y hat not equal to y. This is just f of x. So that's how f is related to this. So for a classifier, I have a rule, apply it to x to a general generic random x, and then compare it with generic y. My loss here is 0, 1 loss. So that's the risk. So this is the probability of misclassifying. So again, f of x. So that's the, let's say, true risk, if you want, the risk. Sometimes called generalization error. I'll get to that. So this is what we want, but we don't know the distribution. So to calculate this, I know I need the joint distribution of x and y, as we have seen before, hopefully, in the Oracle problem. I don't have it, so I use this instead, and you can verify that this is equivalent to like estimating the joint using the empirical proportions, and then using that estimate of the joint to calculate this probability. So it's like P hat of F hat x not equal to y, where x and y are, it's a little bit, I'm gonna like hide this. It's gonna be confusing, but you can estimate the joint distribution and use that distribution to calculate this risk, and that would be the training error. There's this little step there that to avoid confusion, I leave it aside. But that's also another way of doing it, right? So it's equivalent to saying I'm just going to count how many examples I misclassify on the training data. So I have this bullet point here that this often underestimates the real risk. And this often is going to be under the quotation, because it's not always the case, as we'll see. And then I want to elaborate a little bit on that. So the thing is, if you have seen like any machine learning, you know that people split the data into a training set and a test set. So the train classifier on the training set, they don't look at the test set. So that's like some other part of the data. Like for example, if you have 1,000 rows, you keep like 100, like maybe 300 out. You have 700 to train on. That will be your training data, and then you test. Instead of going and doing this on the same data, you're going to do exactly the same thing on the rows that you haven't seen. They're in the test set. So you do the train test split, and you evaluate the classifier on a different portion of the data, other than the part that you train on. So that portion that you use for evaluation is called the test set, or could have other test data set or whatever you want to call it. And the error that you get that way is called the test error. So why do we do that? Why this training error is not enough? That's what I want to get into a little bit. So was there any question? Yes.
Training error should be low, but not shouldn't be 0, right? Because then it's become to 0. We have overfitting.
Yeah, these are all the things that I want to build towards, but I want to get a little bit deeper. So whatever the training error is, whatever it is. So you have a classifier, right? It has a training error, right? And the question is that, is it good to have a low training error? Is it good to like drive it to 0? Try to find a classifier that makes it 0. I'm going to get into that. Like, just ask me maybe after a while. There's another question that I want to answer first. Is this a good estimate? If this goes back to the question that I'm asking. So if this is a good estimate of the error, you should try to drive it to 0. If this is predicting, because I in the end I want this to go to 0, this to be 0. a classifier that achieves zero risk is good, like zero misclassification error. That's what I want. I want this to be zero. I want to find an F such that this is zero. I can't get to see that, so I try to pretend like estimate it in some way for my classifiers. One way to estimate it is this. So if this is a good estimate of that, then it makes sense to make this small, right? If it's not a good estimate of that in general, then it's not a good idea to try to write this down necessarily, right? But let's answer that question first. Is this a good estimate of the risk? Do you remember I talked about the law of large numbers and like averages converging to population mean, right? This looks like an average. First, let me ask you, is it a good estimate? I'm saying that often it underestimates the real risk. It's often too optimistic. The risk that you get is smaller than this, often, but not always. So it might not necessarily be a good estimator. If you've seen like any statistics, it's not an unbiased estimator of the risk. So why is that?
Because we estimate the risk just based on the sample of the data, not the data, not population, based on the sample. And if we use
But
another,
let's say the sample size is very big. My training, so let's say here I have 900 cases. It's pretty big. As much as training, I give you a lot of training data.
data, it's not.
So let's say the law of large numbers. So let me make this a little bit more. So this is an average, right? And I told you that the law of large number implies that the averages converge to population mean. So can I say that this converges to the probability that f hat, let's say x, is not equal to y? So each one of these, so if you have, let me do this. So if I have r hat tr f, so if this f is fixed, non-random, this is going to happen. So I fix one f, let's say f of x is, in our case, like x is female, maybe it's 0 here, x is male is 1, the flip one, not the one that we're looking at, some other one maybe. I don't, that's could be the other one as well. But this not equal to yi. Can I say that this converges in probability to, not like converges as n goes to infinity to f of x not equal y? Is that true? I fix a function like that and claim that as n goes to infinity, as my training data, here I'm not assuming that I'm training f on the data. I give you some f, some from somewhere, right? I fix this f. It's not seen the training data or like the data that I'm using this to value. So is this going to converge to this probability of this, which is what I want? Here you can put I, it doesn't matter because I'm assuming that these are IID from the same distribution as P, and also like this is a generic data. This is a generic, could be unseen data. So whether you put I here or not doesn't matter because they have the same distribution. So is it going to converge to that? If you remember, I can call this some Zi, right? So this is a Zi, it's a binary variable, right? And if they are IID, this is an average, by the law of large numbers should converge to the expectation of Zi. And this should be that. We did some sort of something like that last time to say that, if you remember my discussion here, that, so remember here that these empirical averages are converging to the population joint distribution. That's where we use the law of large numbers. All right, so if you have Zi's IID from some distribution, this is not exactly the distribution X and Y, but from some distribution, then this is going to converge. The average converges to the population mean. And if this random variable is binary, the expectation is just the probability that it's one. Right, so that's the law of large numbers. So is it true that by the law of large numbers, would this be true? Half the statistics is about the law of large numbers. So if you understand the law of large numbers, you understand what you're doing. So if you don't understand the law of large numbers, like, well, you don't understand half the statistics. And I claim that. So can I say if I fix f is like given to you like that, are these random variables binary? 0, 1? Are they going to be independent of each other? They're going to be independent if the xi, yi are IID. These are going to be IID as well, because f is deterministic. This is just like a function of xi, yi. So the first one is independent of the second one, and so on. So this is a sequence of independent, identically distributed random variables. It converges, the average converges to the mean, which is the expectation of zi, which is expectation of 1 f of xi not equal yi. And I mentioned the expectation of an indicator variable is just the probability of it being 1. So the probability that this is 1. Yeah, I'm trying to. And this is the same as writing probability of f of x not equal y, because the pair xy has the same distribution as xi, yi. These are all going to be the same. Okay. So the statement that I mentioned is true. If you fix f by the law of large numbers. So this is true for a fixed f. However, this is not going to converge. So this is going to be R of f, the way I wrote here. So this is, if you remember, this is, so this is saying R hat training of f converges as n goes to infinity to R of f, which is what I want for a fixed f. However, the thing that I have here, my claim is that this is not in general going to converge to R of f hat. And the only difference is that I'm using f hat here, not a fixed f. And f hat is using the data, the same data and the value we want. So why I can't use the law of large numbers to say that? What assumption of the law of large numbers is violated? If I use it for the f hat, which I learned from xi, yi's. Yes.
They're no longer independent.
Why they're not independent? Okay, what was your name? Okay, the last I can't. Akshaz. Okay, I ask you later. So the idea is correct. So if f hat is your classifier that you learn from the same data, this is going to depend on all the data. Okay, because that depends on all the data, all of these. So f hat, I'm going to write something like, let's write it like that. It is here. So f hat Sometimes I write it as f hat of x semicolon dn, and dn is all the training data. So x1, y1, dot, 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 xn, yn. So I'm going to put this to emphasize that this depends on the data as well, which we hide. Okay, so the entire rule is dependent on the data because we use the data to learn it. If I change the data, this function is going to change. Not always, but if I change enough of the training data. So if that's the case, then my training error, if I write it like this, I want to be a little bit more precise, I would write something like that. F of xi semicolon dn not equal yi. And then you can see that this term, each individual term, depends on the entire data. Okay, so each one of these terms in the sum, it's not dependent on that observation alone, but on the entire data sum. Because of this common factor here, they're all linked together, they're all independent. You can't say in general they're independent. Okay, so all these terms are dependent, so I can't, like, there's no law of large numbers anymore. Independence sort of fails, so all of them, all the terms depend on the n, which is the training data, hence the zi's. So z1 up to zn are not independent. There's too much randomness. There's not, this should be f hat. There's randomness in this part and also in this part. And because of the randomness that's in this part, which is the entire formulation of the rule, the entire decision rule depends on the data, but because of this, these are not independent. So in general, this is not going to converge in general to P. Yeah, I'm going to not write P hat because that's another like little story, but this is not going to converge to R of F hat, which is like the population level thing. It's not going to converge to the expectation of these. Okay. So this training is not, even if you increase your sample size to infinity, it's not necessary that it converges to the true thing that you care about. So for that reason, you have to be careful trying to minimize the training group. The training. So what is this? So is this sort of clear to people? So I can't use the law of large number to conclude. So LLN cannot be used to conclude that R hat TRF converges to R of F, which is R of F hat, which is the true risk. But actually, this statement is not precise. If I want to be precise, I would write something like, I should look at this minus R of F hat and say that this does not converge to 0, because this side also depends on n, because F hat itself depends on n. So this is also moving. It's a moving target because F hat changes. But mathematically, I can write the difference. So this is dependent on n. So if you want to be really precise, you'd write F hat n because it depends on the size of the data. And this, we hope that this goes to 0 as n goes to infinity, but this is not going to go to 0. Okay. The reason why is because all these terms that I'm calculating, all these errors, they all depend, they're random variables, binary, but they depend on the entire data set because the rule depends on the entire data set. There is no independence, so because independence sort of fails. Because independence. Forget about this part if it's like on a side, but for the mathematically precise people, because independence is not true anymore, does not hold. Does not hold. Okay. So that's why people split into training and test, because the test set is like each row is independent of each other. So now if I split it, so what you do is you split or you just come up with an independent sample from your data set. I'm going to call it tilde m. The sample size could be m, doesn't have to be the same as the training size. all that matters is that these are independent from your training data. Then I can form the same thing, but over the data. So over this data set that's new, like independent. So this is now going to be 1 over m sigma I from 1 to n. If you want to write it, it's going to be f hat xi tilde semicolon dn not equal yi tilde. So this dn is shared, but this dn is different than these x tilde. So I can condition on the training data, not with fixed dn. Now I'm dealing with a fixed decision rule. Like the training is fixed. So condition on the training data, dn. The rule is fixed. Now I can say that as m goes to infinity, this is going to converge to r, the population risk. Because now this is a fixed rule. It's like the case that I mentioned. You have a fixed function. If you have a fixed function, then this is going to converge because your samples are independent. Once I condition on the training, fix the training. Now, if I have this test set, if the size of the test set starts to grow to infinity, because my rule is fixed by the training, conditional training data, I can now use the law of large numbers, conditional training data, this converges to what I want, okay? The independence of this, and that allows me to treat this as a fixed rule relative to the test data set. And as the test data size of the test data set goes to infinity, the law of large number kicks in and allows me to conclude that this is true. Does that make sense to people? Yes.
So you show that the training error in general is not converge with error.
Yes.
But is there any reason that the training error is under? Can it be overestimated?
It can overestimate, I'm not saying, but generally it's underestimates because you deliberately try to make it small. And you would like your training error. So you could try to maximize your training error if you like. But the reason why I'm saying is often underestimates because by design, you try to minimize it. As we'll see, all of the machine learning algorithms try to minimize the training error. The way that they learn, there is a class of classifiers that operate by trying to find within a class of classifiers one that minimizes training error. These are called like usually empirical risk minimization techniques, like neural networks, like logistic regression, SVM, all of them trying to minimize the training error. Because you try to make it small, it's going to be usually smaller. Because you try to make it small. I'm not proving that it is like that, right? To see that you can actually drive it to 0 to get to the point. So what was your hand? Oh, no, okay. Anna mentioned, so in this case that we have, let me maybe pause, see if people understand, and I'm going to keep that example. If people understand this. So if someone asks you why you split into training and test, what would be your answer? Yeah.
So you can see how you want the performance of the
Yes, that's like the machine learning answer. If you want to be like a deep statistician, what is wrong with seeing the performance on the scene data? Is there something wrong with the scene data? If you want to be like give an answer so that you like they hand you the job immediately on the spot. It's not a consistent estimate. So training error is not a consistent estimate of the population risk. And you can also show that no, it's not unbiased. So even the expectation is not going to match. So, but it's not, the reason is that it's not going to converge in general. Even if you increase your sample size, the training error is not necessarily going to converge to the true misclassification rate, which is the risk, which is the population version. And the reason is because of the dependence. Because you're evaluating the same classifier on the same data. The classifier is learned from the data, you're evaluating the same data, so there is a lot of dependence in forming this sum. So each term here is dependent on the entire data set. Okay, so the law of large number does not hold. And so if you understand this at a higher level, why you do split. Because this is not going to be consistent statistically. Yes.
But the law of large numbers does say that if you increase the number in your testing data,
Yes.
that will be a better.
Yes, that starts to get a better. So the test exactly. The law of large number tells you fix your training data. Fix your training data, train your classifier on the training data. That's fixed. Now you have this test data and you can ask for more. Someone's just going to give you more. And then you evaluate on the test data, you evaluate on the bigger test data and the bigger test data. As long as that's independent of training, that error that you get is going to get closer and closer to the true value by the law of large number. Right? That if you understood this argument that I mentioned about the fixed f, once you fix your training data, it's like a fixed function. Once this is fixed, there's no randomness. So conditioning and training data, this is fixed. Then these things only, the randomness is only on the data that you're evaluating on, which is the test data, and that randomness, each term in that random series here, let's do it here. So once I fix the end, this rule is fixed. Now the randomness only is these tilde things. So the tilde is the test data, and they're independent. So all these terms are going to be independent. So this is an average of independent. I think this they're muted quantities. So this is going to converge to the expectation, which is a conditional expectation given at the end. Which, well, you just assume that the training is fixed. So no conditioning is necessary. Then this is going to converge to the true risk. Okay, so you increase your test size, you get a better estimate, like a progressively better estimate of the true misclassification rate. Okay, if you keep increasing your training set data and you're evaluating based on training error, it's not going to necessarily improve. It's not going to improve your estimate of the true misclassification rate. Does that make sense? It's an important point. I probably can come back to it. This is not the entire story. There's an interesting, there's a very interesting thing that happens here. In this example that I'm talking about, in fact, the training error converges to the population risk. You don't need to split. And that's what I want to go back later, but that's like the next level. It's like, you understand this, you're like already level, I don't know, 10 versus like a machine learning person, level 1, level 10. If you understand what I'm going to tell you next, will be level 50, like out of level like 1,000, I guess. No one knows what the upper limit is, but in this case, you actually don't need to do a split, but I want to first understand you need to do the split. Okay, why we need to do a split? Because we can't use the law of large numbers. If you want a reason, the reason why we're doing all of this is because of the law of large numbers. We're going to be sure that as the sample size grows, things converge to what we want. But for the training error, we can't be guaranteed that. At least the law of large number cannot guarantee us. Maybe some other high power result can come in and guarantee that in some cases. But this is not going to guarantee us. Okay. Does that make sense? Questions? Yes.
So before you fix the training data, how do you get the optimal size of the training data to make the training data fix to that?
So there's no relation between M and N here. So the size of the training data determines the quality of the classifier. The size of the test data determines the quality of your estimate of the risk of that classifier. I can have a very bad classifier whose risk I know very well. Okay. This is the distinction. Okay. So the size of the training data allows you to improve your classifier. If you increase your test data, you can improve your estimate of the risk of the classifier. These are very different things. I can have a very bad classifier whose true risk I know very well. And I can have a very good classifier whose true risk I know very badly, like poorly. They're both possible. Does that make sense? So this M and N have no relation. They're trying to do different things. So the size of the training data allows you to we'll see, allows you to improve your classification performance. The true, like the R, the true R. But I don't know the true R, I want to estimate it. The size of the test allows me to estimate it better. If I increase M, I'm going to increase improve my estimate of the risk of the classifier, whether it's a good classifier or a bad classifier. I can do it for the majority rule. Majority rule is just zero training error. Sorry, zero training data. Majority rule does actually not zero training. Sorry, that would be really bad. So zero covariate information. So you can have training data, zero covariate information. It's a bad classifier. Majority rule is generally not necessarily bad, but generally not the best classifier. But I can know the risk very well if I like take the M to infinity.
So, like in practice, do we alter the N to find the best classifier first, and then alter M to kind of research the risk of that optimal classifier?
So in practice, there's a lot of things could happen. So if you understand this is the story, right? In practice, you get like a limited amount of data, and then you have to decide which part you want to use for training, which part you want to use for tests. I'm trying to say that first try to understand, let's say you have unlimited data. Okay, at least for the test, you have unlimited data. Then this is the case. So in practice, how should like at one point should we switch? Should I keep like 90% of the data for training, like 10% for tests, or like do like 70% for training, 30% for tests, 50% for training, 50? That's a different story. Okay, and there's no good answer there. At least I don't know a very good answer, but we'll come back to this later. You can try to use all your data so that at least every piece of data appears once in test, once in training, so that you have used. So the issue with splitting your data is that you lose the statistical performance, because if you use all your data to train, you can do better. So we'll see. We haven't seen this, but this is something that maybe later we'll see. Maybe that if you increase your training set, the size of the sample size in your training set, generally you can do better. You can approach the optimal rule. Sort of, you can see you can estimate the probabilities. At least in this case, that's the case. In this the case where we have a discrete covariate, you see that we got the probabilities from the data, and by the large numbers, those probabilities are going to converge to the true probabilities as the training set, like sample size, goes to infinity. So I'm going to approximate the optimal rule better and better. So the question is that how much I want to approximate. At some point, in this case, more training doesn't matter, because the rule is going to be very simple. You saw that almost with 10, a sample size of 10, we managed to get a very close. I think Alex did some sort of calculation last time, except for the case of the female. For the male, it was correct. So for the female case, we're in the boundary case. If I have like maybe 10 more rows, maybe 5 more rows, a few more females, if I see, I get the decision rule, which is similar to the decision rule that I got with like 1,000 rows. So that I have here like 982. And as an exercise, it's another good exercise to try to see how much training I need before the rule doesn't change anymore. Okay, so if I'm just doing the training based on this, like classifier only takes the 6 column. 1, 2, 3, maybe this is not enough, but at some point, I don't need any more samples, because the rule was fixed. Like the probabilities are good enough that the rule is not changing. So then the rest I can use for tests, right? So this is a very good example. If you understand this, you understand a lot, because you don't need to always like make the most complicated classifier. There's no reason to like try to estimate those conditional probabilities to the 10th digit if there is a big gap between them. So you can already see, for example, this is like 0.75, and we'll see. Like I can try to estimate, like give an estimate of the error, and at some point there's like I'm gonna just change, like here it's gonna like maybe go like to 81, but at some point I'm just gonna improve to like the 3rd digit here, right? So like 0.81, 0.81, 2, maybe 1. That doesn't matter because it's bigger than 0.5, as long as I'm bigger than 0.5. fine. If it's like, it turns out to be like, this is 0.49, maybe you have trouble. You have to gather more data because you're at the boundary of the decision rule. Here, the decision is very simple because you're away from 0.5. Once you're sufficiently away, you know that you're done. So you don't need to worry. Does that make sense? So you don't need to estimate these probabilities to the like the 10th digit to do the optimal classifier. Yes.
If you're at, if we discovered that you're like at the decision boundary, would that mean that you need to add more data than this?
Generally, yes, unless it turns out that at the population level, there is this ambiguity in data. But yeah, generally, if you're, if this turns out to be like very close to the boundary, it's reasonable to try to collect more data. Or I'm not going to give the answer to the exercise, but you have to decide, the decision is going to be murky in that case. So you can flip a coin and decide. But if you want to do a better job, it's reasonable to collect more data. Yeah, it might not go away. It might be like at the population level, there is this ambiguity. There's no reason. It could be that the optimal Bayes rule has this ambiguity in it, but oftentimes it's not like that. Okay. Yeah. Oftentimes it's not going to be exactly 0.500000 all the way. It's going to be at some point like there is a 1 maybe here or like, and then you can decide. Yeah. Okay, any other questions? So this is like a fairly deep topic. If you understand it, you understand a lot, and then you can understand a lot based on this example. If you have any questions, let me know. I'll come back to these ideas again. Any other question? So it's not always, to answer, it's not always going to help to increase the training. Generally, it's good. And we'll see, for example, you have continuous covariates. Often it helps, but you can see in these discrete cases, you may not need. If all your covariates are discrete, and like there are a total of like 6 levels among all of them, then at some point your decision rule is going to be fixed. There's no reason why you have to increase your training data. Good. Any other questions? So later on, I'm going to come back to this idea that in this case, actually, the training data is going to converge to the true risk, but that's like, as I mentioned, something you have to first understand this, understand why that happens. So that's a surprising result. This is not surprising. This is often happens. Training error is not a good estimate of the true risk. So can you give me an example? Okay, this is what I wanted to say. So can you give me an example? Suppose that x's are continuous. Suppose we're doing the age. I give you this data set. Ignore the 2 rows that have NA in them. I want to classify based on age. Can you give me a classifier whose training error is 0? Always 0. My claim is that if you're like, you can't do it, for example, based on these 2 columns. But if I want to train a classifier in age, I can find a classifier that always has 0 training error. And you can imagine that that may not be a good choice. How can I do that? That's where you see you can underestimate the error severely. Sorry? That's what called overfitting, but how can I achieve that? You don't know it's overfitting. It might be actually the actual risk is 0, but generally it's not. You say overfitting when you're fitting too good to the training. So your training risk is much smaller than the population risk. The smallest that it can be is 0. 0 is classification. So if your training is 0, it's likely that you're underfitting, unless at the population level, you also is the Bayes risk is 0, basically, which is not. But how can I achieve something like that? Yeah.
You use the whole data set as the testing data set?
No, there's no test. I have a training data set, and I want to evaluate, I want to compute the training data, sorry, the training error. So I don't need a test. I have a training data. I want a training classifier that has 0 training error. And I can always do it. if this is continuous, not if it's discrete. Yeah, maybe think a little bit about this. That shows you one of the issues with the training error.
Where you have like a small enough data set.
No, a small data set, big data set, you can always do it if the covariates are continuous.
You don't repeat the contract.
Suppose I have a data set whose so I'm trying to we use this column to train the classifier. We use this covariate. Suppose I use a covariate which is continuous. By continuous I mean with probability 1, there's not going to be a repeat of the values. So every time I observe a new case, it's a new number. So if you have a continuous distribution like normal, every time you draw from it, you see a new value. You're not going to see multiple like repeated values. So if that's the case, so if I want to correct, suppose you got this column, this 8 column this is not going to be like that because it's still discrete. So you can't have 2.3, 23.01. You can have it if you like measure the age up to like the true time, right? One like this many years, this many like days, this many hours and seconds, and assume that age is like this. We don't have that resolution, but suppose that the age is very like a unique real number. At that time, at that moment in time, each one, it's like the age is like a real number, right? So this could be 23.101 and then 4.05, whatever. So they're not going to be repeated. So every time you have a continuous value, like a normal value, every time you draw it, you get a new number. The probability of observing the same number is 0. If that's the case, assume that this is the case for this. I'm saying that no matter how many data points you have, no matter how large your training is, you can always find a classifier that has 0 training error. Yes.
So you said all the ages are unique, right?
Yes.
So we just need to have a decision tree that has many nodes that we have all the situations and we discuss every situation.
Yes, yeah. A decision tree like that, or just simply stating, I'm just going to map every age to whatever I observe in the training data. So if it's 27, I'm going to say, so my decision will be f of x would be, if x is 27, it would be 0. If it's 21, it would be 1. If it x is like, forget about the NA. If it's 4, it would be 0. I'm going to go count like for every value in the data set. I'm going to just record the decision as my decision rule. It's like a big table. It's like hard-coded values. And because, as I mentioned, if the random variable is continuous, with probability 1, these are not going to be the same. If you have repeated values, you have an issue. If I observe x27 like 4 times, then there might be like discrepancies. But if this is the case, which is a continuous variable with probability 1, I don't see repeats, then that would be my rule. So x23. And you can see that let's say x. Unfortunately, here we have 27 twice. But let's say this is 27.1. This is 27.5, for example. We're just not seeing it. But this classifier is going to be guaranteed to produce 0 training error, and you can specify it however you want elsewhere. Leave it undefined or just 0 or randomly pick. So you're guaranteed to have a training classifier that outputs 0. Sorry, has 0 training error. But intuitively, you can see that this is probably not good. Right? This is that's what I said. You can often underestimate the risk. You can severely underestimate the risk. This is an example where the classifier is too complicated. So if you're allowed to have very complex classifiers, if you're allowed to do anything you want with any x value you get, then it's likely that you can drive your training error to 0. Yes.
Is the reason that it wouldn't be discrete is because discrete values could be repeated?
Yes, exactly. So I have 2 choices here. I can't. That's what saves me here. So if I assign male to 0, then I can't assign male to 1. So I have to decide which one. And then somehow you aggregate that there's some aggregation information. You have to decide which one to do, and like unknowingly that helps you statistically. Okay, and the data is like forcing you to not like shoot yourself in the foot. Okay, which you can do with continuous variance. That's why we started with the discrete case. Yeah, that's the question. Yeah, try to implement that with this column and you see you can assign a value to each one so that you can achieve zero training error. And that's basically why the training error is a good estimate here, because you can't force it to go to zero. But we're going to get I'm going to give you hopefully a deeper understanding of why the training error is actually good here. So there is a connection between the complexity of the class of classifiers that you choose and between that and the fact that training error is a good or a bad, not necessarily, but not necessarily bad, but not necessarily a consistent estimate of the population. So, but I'm going to do it in the next session, not today. So as not to come, maybe in another session. Today we see that the training error is not good. Okay. Later we see that training error could be good. Good. Questions? So that's what we do with for evaluation. There's a training error, and another reason why it's called a training error, because usually you use it to train the classifier, as we'll see. It's a quantity that you try to minimize to learn the classifier. We didn't try it that way yet. Implicitly, we have done it, but it's not obvious probably that we try to minimize the training error implicitly in the background, but we'll see that more. And we use the test set to have an independent sample so that we can gain some understanding, so that we can get a good, unbiased, consistent estimate of the true risk, which is this classification rate in this case. Okay, where do we get the test data? We split it into two parts. Usually you use one part for training, the other part for test. How much you have to choose, that's a different story. Let's not get into that. I just want you to show you. So if you do it, I'll probably decide as a homework problem. If you do go and calculate the actual, so I've split this into 982, I guess, and then this is the test error, the test data set, 327. So the actual data set is like about, probably, I guess, near like 1,300 rows. So I already split it into half, like not half, like I guess 70% for training, 30% for, roughly 30% for test. This is the test data, and we evaluate our classifier that we learned, the one that's based on the correlated sex, on this, and it turns out that this is the test error, 0.217, and this is the training error. We can calculate this, and they're very close actually, which goes back to the point that in this case, training error is not bad. And this is very close to the thing that I mentioned, like from the Oracle, which used actually all of the data, which was 0.22. All of them are very close. So training error, test error, in this case, it's not bad. So what is generalization error? The generalization error is another name for the risk. Okay, if you see generalization error is exactly what I mentioned, risk. The reason why it's called generalization error, because you're evaluating your classifier on a generic data that's independent of you. So this thing is independent of everything else, but it's coming from that is the true distribution. So you're evaluating a generic random point. You can say unseen or something like that, but either unseen or like independent. Statistically means independent of the training data or your classifier. So you're evaluating it on this new data set. So that's you're trying to see how it generalizes, how it performs. Generalizes means performs on unseen data, on future data, on independent data. That's how you measure. This is exactly the risk. So it's another name for the risk that we use. So it's not nothing new. So you also know what generalization error is. So you're using the test error to approximate the risk or estimate the generalization error. We are often not using the training error. So training error underestimates often the generalization error. So just generalization error and risk are synonym in our case. Okay, one more point. Any questions? I just wanted to get a little bit of this before the end of today's lecture. So now I want to add another covariate here. So I'm going to add the p-class, still discrete, has 3 levels. Now my covariates are like in class. I can, as I pointed out last time, you can try to estimate the joint distribution. You can go over all the cases and evaluate the joint distribution. This would be a 2 by 2 by 3 tensor. Just saying like an array that has, it's like a matrix but repeated along another dimension. Another way of viewing it is all the combinations of these 2 covariates, there's 6 of them. So like one is female, male, the other 1, 2, 3. So I get F1, F2, F3, M1, M2, M3. So I can treat this thing as a new single discrete feature with 6 levels. So everything is back to the previous case. We can repeat this. I can look at the joint distribution. So joint distribution would be like y here and this new feature here. So that's my y and this is my x. Okay, has 6 levels. And then I go and recalculate the get the estimate of the joint distribution. The way I do it is just count, right? So proportions, and this turns out to be my joint distribution. And then I can use this joint distribution, calculate the optimal rule, like an estimate of the optimal rule, which can be written as a decision tree. So it turns out if you do work with these softwares, they're going to split based on a single level. So if you ignore this middle split, we have just split based on sex and based on class at the end, like class 1, 2, 3, and class 1, 2, 3. So we have all the, also these give you probabilities of, for example, y equal 1, given that this new x is M3, male M3. This one is probability of y equal 1 given x equal M2. This is, for example, the probability of, these are estimates. Y equal 1 given x equal F2, and so on. Next time I'm going to come back and calculate some of these probabilities based on this table, see if you guys can follow. But basically, we have the joint, we can calculate these conditional probabilities, and there's 6 of them. And this is our regression function, basically. So regression function, this is like eta hat of M3 if you want, and so on. So we have these 6 numbers, and then we can write our decision rule, which is going to be like a function that takes all of these 6 cases and decides 0, 0, 0, 0, 0, 1, 1, for example. That's the decision. Okay, so next time we're going to come back and look at this at a bit more detail. Thank you.
So